Hi, Assalamualaikum warahmatullahi wabarakatuh. This video is about the introduction to linear transformation. And before we dive into this topic, here is a quick recap on what is the idea of function, domain, codomain, image, and range. So basically, V here, this is a capital V, big V. It is called a domain of T. So T here is the function. It is a link between here V and W. So V is called a domain and W is called codomain. So here is codomain and here is domain. Notice that we have a small v, so small v is inside the big V. So small v here is the element of V. So this is the small v. And when you give this to a function, so when you consider this as an input to the function t here, you will get a specific result. And we call this result as W. Now the result here has a specific name and we call it image of V under T. So here we have V and you supply this into a function T. So this is the result when you supply V into a function. This result is also known as the small w, and the small w here has a name and we call it the image of V under this T transformation. So let's say you have many possible inputs. For example, here is another input. We can call it, for simplicity, is V1 is another input here. V2 is another input. So if you keep on supplying this to the function here, you will get all sort of possible images. For example, V1, if you supply into T, it could be mapped into this part. So this is could be W1. V2, if you supplied it into this function, then it could be mapped somewhere here. So the list of all images here are called the range of T. So that is the idea of function, domain, codomain, image, and range. And what we did just now is sort of transformation. We transform something here using this transformation function and we get something else. And here is an example. We have a function that is going to transform this vector space here with 2 dimensions into another vector space also with 2 dimensions. And we have a vector here defined as V1 and V2, 2 dimensions. So we have 2 components here, the first component and the second component. And we are going to transform from this vector space to another vector space using this idea here, where you are going to give this as an input into the function. So T here is a function, so you supply this into the function here, where the result is going to be defined as such. So for the first position here, it is the result when you have V1 minus V2. So what is the result? And at the second component here, it will be the result when you do the process here, which is V1 plus 2 times V2. And of course, this result here is known as image. Okay, so this is the result. Okay, so as a simple example, let us consider finding the image of this given vector here. Therefore, what we have to do is we can then supply this vector into the function given. So here is -1 and 2. And notice that I'm just going to put a little bit of notation here. So this is V1, sorry. Okay, this is V1 and this is V2. And according to the rule given here, the result is going to be, well, v1 minus v2, so negative 1 minus 2 is negative 3. So v1 plus 2v2, so negative 1 plus 4, which is going to be 3. So this is the image of this particular vector given here under this particular transformation. Okay, next we are going to find the pre-image of this one here. So what is pre-image? Pre-image is, well, the value of v, the value of our input, if you would like to think that in particular way. So this is the input, and we have got image. So here is our image, and you want to find what is the input that gives us such a result. Therefore, we can think of the information given here as something that looks like this. We might have a vector which is v1 and v2. We don't know what that is, but the process here, according to the rule, is v1 minus v2, v1 plus 2v2, and if you supply v1 and v2 in this particular case, we get the result of negative 1 and 11. So this could be your starting point, and based on this you can create equations. So here is the first equation. We have v1 minus v2 must be equal to negative 1. Therefore, I can say v1 is negative 1 plus v2, and I'm going to call this equation 1. Next is this part here. Okay, we can have v1 plus 2v2 is equal to 11. So this is equation 2, and we are going to substitute 1 into 2. Therefore, negative 1 plus v2 plus 2v2 is 11. And here negative 1, 3v2 is 11. So v2 here, well, you can see 12. So here 12 divided with 3 is going to be equal to 4. Okay, so I'm going to call this 3. And then next is, I'm just going to substitute 3 into 1. Therefore, v1 is negative 1 plus 4, which is equal to 3. So here are the values of excuse me, here are the values of v1 and v2. Okay, and therefore the answer to this question here, okay, you can write down the answer here. I'm sorry for going all over the slide, just don't have enough space for this one here. So therefore for this one here is the pre-image of vector w here is equal to 3 and 4. Okay, so this is just a simple example to illustrate the idea of image, pre-image, and so on. Oh, actually I have a space here. Okay, never mind. All right, now what is this chapter all about? It will just focus on functions from one vector space to another, and in this process here we will preserve the operations of vector addition and scalar multiplications, and because of that it is called linear transformation. Functions that do all this are called the linear transformations, and we can check whether this particular transformation is a linear transformation. Okay, you can transform actually from one vector space to another, even though here you can see the dimensions are different. It could be here is n and this is m, doesn't matter. They could also have the same dimension, but what I'm trying to say is that this t here is a linear transformation if it fulfills two conditions. So here is the first one, where it says if you have two vectors, u and v. So these two vectors are in that particular vector space. So the transformation here, if you supply u plus v into the transformation function, the result is the same as if you decided to do it separately. So if you consider adding the vectors first, find the transformation, the result is the same if you do it separately. For example, you do one vector first, get the transformation of one vector, tu, plus do it for another one, and you just add them together. So that is vector addition. So you preserve operations of vector addition. And here is related to the scalar multiplication. So this one, C is scalar. So when you have it, you can just consider taking out C from the transformation function, and then you just focus on finding the result of this. Okay, what is the result when you supply vector v here into the transformation function? What's the result? And then you multiply with the constant scalar. Okay, right. Bearing that in mind, here is a particular example related to how you can prove that the given transformation function here is a linear transformation. Again, in order to do that, we have to go back to these two conditions here, and we must be able to show that they are true. Okay, so that will be our starting point. Okay, so in order to be a linear transformation, so number one is you have, well, you can see here, this is vector v. So we try use different alphabet, even though what is given here is originally u and v, but we can choose different alphabets to denote the vectors. And we can say that in this case, I'm going to show that vector x and vector y, if you consider this, it should be the same as this. So this is the first condition that we have to show. Now the reason why I'm going to use x and y is because here is already given as v, and we just don't want to use v anymore. Of course, if you want, you can use u and x or whatever. Okay, now that is the first condition. The second condition is you have to show that when you have input of scalar and vector and given it to a transformation function, the result should be equal to C times with this guy here. Okay, so these are the two conditions that we have to show, and in order to do that, we are going to start creating these two vectors first. So we're going to define x, so let x is equal to x1 and x2. So you can see the resemblance of this one with what is given here. Okay, and we're going to let y equals to y1 and y2, and we're going to start with proving condition 1. Okay, so here is some notation proving condition 1, and I will start from the left hand side. So this is what I'm going to consider. So from left hand side, we have t x, so vector x and vector y, and this is equal to having t. What is vector x? Vector x is given as x1, x2. What is vector y? y1, y2. So this is quite straightforward. Just replace what is vector x and what is vector y. Next, we're going to do the operation inside here. So it will be t x1 plus y1, x2 plus y2. And I'm just going to give a bit of notation here. So I'm just going to say that this is little note, okay? So this is just V1 and this is V2. And I'm just going to follow this idea. So V1, V2. So we know that V1 minus V2 is the rule given here. So maybe for reference, I'm going to write the rule as V1 minus V2. And the other one is V1 plus 2V2. Okay, so based on this rule, so I'm just going to say this, the rule, the transformation function, or the rule for simplicity. Therefore, if I have this result here, this is V1, you can think of it as V1, and this is V2. And according to the rule given here, the result will be looking like this. Okay, so we have x1 plus y1 minus V2 is this guy, so x2 plus y2. So this is what's going on here. And then for this part, V1, which is x1 plus y1 plus 2, V2 is this guy, so x2 plus y2. And try to expand the whole expression here. So you will have x1 plus y1 minus x2 minus y2, x1 plus y1 plus 2x2 plus 2y2. Now, in order to separate them, so you see that we are looking for, so this is the left hand side, and we are looking to be able to separate x and y. So we need to think of separating x and y, which we can then consider grouping all the x's together and the y's together. So here I'm going to group based on this. Well, let me just highlight. So this is x and x. Since this is just positive, negative, addition and subtraction, you can, change the position. Okay, so it is not going to be problematic if you do that. Therefore, what we can do is we are going to have x1 minus x2 grouped together plus y1 minus y2 grouped together. Okay, we change the grouping. Here is different grouping, you can see that, and now we change the groupings. And similarly for this part here, we're going to put x's together and y's together. Therefore, x1 plus 2x2 plus y1 plus 2y2. Okay, and I'm just going to continue right here. Therefore, because this is like matrix, and you can separate them, so it will be like this. You can have it as x1 minus x2, and on this part plus y1 minus y2, and you can see when you add them together according to the first position here, this is the result that you will have. Okay, so you can do that. Now here it will be x1 plus 2x2, y1 plus 2y2. Okay, now what is this thing? So does it look like we have x1 x2 v1 v2? We go back to the rule given, x1 to x2 v1 to v2. Yes, it looks the same. So therefore this is the same thing as having t x1 x2. Okay, because this is what is given by the rule. So the rule here says if you have v1 and v2, this will be the result. But here we have x1 and x2, therefore for this part here it's going to just replace v with x. Similarly for this one, you can see it looks similar to the rule given here, y1 y minus y2, v1 minus v2. Yes, y1 plus 2y2, v1 plus 2v2. So we know that this must be v1, sorry so that must be y1 and y2, and we can simplify that further to just say this is so this is x, vector x, plus this is vector y. And we have managed to show that from the left hand side we do all the process here, and we are able to show that it is equal to the right hand side given as such. So condition 1 is fulfilled. Okay, next we are going to try and prove the second condition. So here is proving the second condition. And again, I'm going to start with the left hand side. So from left hand side, we have this notation. We can start with Cx bar. And I'm just going to replace what is Cx bar. So Cx bar is C and x bar is x1, x2. So x bar here is vector x actually, okay? And we're going to do the process here. We do the inside and solve what is inside first, okay? So here we have, well, Cx1, Cx2. And remember what is the rule given. So the rule here says if you have this function t, which is this one, and you supply a vector v1, v2, so here is the values v1, v2, the result is going to be v1 minus v2, and then v1 plus 2 v2. So based on this notation here, if you don't want to get confused or whatever, just put a little bit of note somewhere here so you know that this is actually v1, this is actually v2, and we're just going to follow the rule given here. Therefore this becomes the result here, we follow this idea. So we're taking v1 minus v2, so the result is going to be Cx1 minus Cx2, and then for this part here it will be Cx1 v1 plus 2 v2, so plus 2 Cx2. Okay, now what we need to show is we need to show that C can be taken outside of this operation, and to do that you must be able to factor C out, and we can do that. We have C over here and C over here. This is something as Cx1 minus x2. Okay, we can write it in such a way. Here is C x1 plus 2x2. And we have C on both components. That means you can take it outside this matrix notation here. So we have C. Hang on. So here we have C x1 minus x2. This is x1 plus 2x2. Now go back and look at the rule given here. They look similar, don't they? So here is x1 minus x2, v1 minus v2. x1 plus 2x2, v1 plus 2v2. So we know that this is equal to C times with T, where the input here is x1 and x2. Okay? And that can be written as C x bar, which is x vector, T with x vector as an input. So we have managed to show the left hand side here is equal to the right hand side given here. Alright, I hope you are comfortable with the way we're proving things, because here is another example, and I think this is the last example, and we shall end the video after this example, okay? Right, for this one here, you can see that right now we have a transformation function t, and it transforms something from vector space with 2 dimension to 3 dimensions. So you can see here the input is 2 dimension, but then the result here is 3 dimension. So this is the output or the image, okay? Right. Again, to show that it is a linear transformation, what you need to do is you need to show that we have 2 vectors, and they preserve the idea of vectors addition. So notice that here we have x and y, and for simplicity we can also have 2 vectors, so we can just say like t okay, I'm just going to talk about the rule first. Okay, let's just ignore that part first. Okay, so here we have t vector u plus vector v. There's no vector v, and so we can use it. We're not going to get confused with all this. Okay, we must show that it is equal to t with input vector u plus this one with input vector v. And the second condition is c vector u here must be equal to this on the right hand side of this equation. Okay, all right, for that reason we're going to create these two vectors u and v, and so I'm going to let vector u here be represented with maybe x1 y1. Look, I'm just following this notation. Here we have x and y, and therefore for this one I'm going to follow exactly like x and y, but maybe with something different. So to denote something that is slightly different, I just use x1 and y1. Okay, and I can call vector v, and this is equal to x2 and y2. So there are different items here. This is x1, this is x2. X here is also different. Okay, so this is like the rule given. Right. Therefore, we're going to start off with proving the first condition. So here is the first part to prove the first condition. So proving the first condition. And I'm just going to put a little rule on top so that we all can refer to it. So here we have this function given as x and y as the input, and the result is going to be a vector space with 3 dimensions, x to x minus y, and here is 3x plus 4y. Okay, so from the left hand side I have this expression here. Okay, and then I'm going to just substitute what is u and v. So u and v is just x1 y1 plus x2 y2. Sorry. Okay, so this is the starting point. Then what I can do is I can consider solving what's inside this bracket. So I have t x1 plus x2 y1 plus y2, and just for the sake of trying not to make mistake and whatever, I'm just going to put this little note to myself saying that this is actually x. Okay, I'm following this here, and this is just y. Therefore, if we follow the given rule here, when you have this kind of input, the output or the image is going to be, for the first component here is just x, which is just this one, x1 plus x2. The next one is 2x minus y, which means 2 times this guy minus y is this one, so minus y1 plus y2. Okay, and here we have 3x plus 4y, so 3x, 3x1 plus x2 plus 4y1 plus y2. And the next sensible step that we have to do is we need to expand the whole thing, okay, and see what sort of things that we get. So here we have x1 plus x2. For this one here, if you expand it, it becomes 2x1, 2x2 minus y1 minus y2. And here we have 3x1, 3x2, 4y1, 4y2. Okay, in order to proceed to proving this first condition, you have to see that the first condition here relies on being able to separate u and v. So in other words, being able to separate, in this case, x1 and x2. So y1 and y2. So all the ones have to be on one side, all the twos have to be on the other side. So here I'm just going to label it. So 1 have to be together, grouped together. Okay, because it represents this particular vector u, and then all the 2 have to be together on the other side. Okay, so that's the idea. Now, if you do that, I'm just going to continue on this side. You will have something that looks like this, x1 plus x2, okay? And then I have 2x1, so I'm just following the red sign here. So 2x1 minus y1 going to be together, plus 2x2 minus y2, okay? Grouping all the reds together and the blues together, yeah? For this one here, I will have 3x1 plus 4y1 plus 3x2, 4y2. Okay. Next, we can just totally use different brackets. Okay, so we can use different brackets for red and blue. So here is all red and here is all blue. Therefore, we can have x1, 2x1 minus y1, 3x1 plus 4y1 plus x2, 2x2 minus y2, 3x2 plus 4y2. Now, based on this, I hope you can see that the rule here applies. This is x, so this is x, x1 and y1, so x1 and y1, just x1 and y1 on one side, x2 and y2 are on this side, and they follow the rule given here. Therefore, you can just simply write this as t of x1, y1, and this is t of x2, y2. The input here is as such. And what is x1, y1? x1, y1 is u, vector u, and x2, y2 is actually vector v. And there you go. We're done with proving the first condition. And let us move forward and try to prove the second condition. So for this condition here, well, from the left hand side, I have t, and here is c, vector u, which is equal to, I'm just going to substitute what is u, c, u is x1, y1, okay? Right, and then do what's inside the bracket. So I have c, x1, c, y1. So what is the result when you have input as such? The result has to follow the rules given here. So what are the rules? The rules says that the first part is going to be x. So this is x, cx1. The second rule is 2x minus y. So here we have this is x and this is y. So 2x minus y means 2 times with cx1 minus cy1, okay? And for the third position here, we have 3x plus 4y. So 3x, 3cx1 plus 4cy1. And we know that we need to be able to prove that c can be taken out of this process here. So therefore, bearing that in mind, we should be able to try to factor c out. So how to do that? We can write it in this way. So C times x1. And then here we have C and C. That means we can factor C out. We have 2x1 minus y1. Similarly, here we have C and C. So factor that out. 3x1 plus 4y1. And this is a matrix C, C, C. So we can just take it out of this matrix. C. So we have x1, 2x1 minus y1, 3x1 plus 4y1. And I'm sure you can compare this with the rule given here, and you will be able to say that this is equal to C times with T x1, y1, and this is just C with input of vector, sorry, not x, vector u. Okay, so this is just given by t, and the input here is vector u. Okay, all right, that's all for now, and thank you very much for watching. I'll see you in the next video with the idea about the standard matrix of linear transformation.